This is a walkthrough of an A-level Further Mathematics, Further Statistics 2 paper. Question number 1. A magazine editor believes that shorter articles are more likely to be read than longer ones. She asked a large random sample of subscribers which of the 10 articles from the magazine they had read. She then ranked the articles from 1 to 10, with 1 being the article read the most. The editor then counted the number of words in each of the 10 articles, and her results are given in the table. So you can see the results in the table here. Articles labelled from A to J, read rank labelled from 1 to 10, and the number of words in each of those articles. Part A, calculate Spearman's rank correlation coefficient for these data. So for this part of the question, we are going to need the formula to find Spearman's rank. But before we can attempt this part of the question, we need to rank the number of words for each of these articles. So I've added a word rank row here in my table, which I'll fill in a moment. Now, because this person believes that shorter articles are likely to be more read than the longer articles, then also looking at this piece of information, that the articles being most read are ranked number 1, then I want to rank my shorter articles 1 to the longest article 10. So here's my word rank part of the table filled in. I now need to add another row, and I want to add a D row, which is going to be the difference in the ranks. So let's just put this down here and we'll get that filled in. So I'm going to do the read rank minus the word rank and see what I get. So remember, you may have some negatives, keep them as negatives. So I'm going to have 4 minus 3, which is 1, 6 minus 10, which is going to be negative 4, 1 minus 1, 0, 10 minus 9, 8 minus 8, 2 minus 2, 7 minus 6, 5 minus 7, 3 minus 4, and then 9 minus 5. So now I can calculate my Spearman's rank, R sub S, which is going to be 1 minus 6 times the sum of all these differences squared. So I will add a difference squared row. You don't need to. The numbers are easy enough to work out those differences squared manually, but I'll just add it in so that it makes it really clear exactly what we're doing. And so the differences squared are going to be, let's choose a different color, 1, so that's 1 squared, 16, negative 4 squared, 0, 1 squared is 1, 0 squared is 0, 0 squared is 0, 1 squared is 1, negative 2 squared is 4, negative 1 squared is 1, and 4 squared is 16. So 6 times by the sum of my differences squared, so that's going to be 1 plus 16 plus 0 plus 1 plus 0 plus 0. So write in the zeros as well. Plus 1 plus 4 plus 1 plus 16. And that's all going to be over, if I can draw a straight line, n times by n squared minus 1. Now, n in this case is 10 because I've got 10 articles. So it's going to be 10 times by 10 squared minus 1. 100 minus 1, or 99. Let's put that all in our calculator and see what we get. So we'll have 1 minus 6 times by 40, that's the sum of my differences squared, divided by basically 10 times by 99, so 990. That's 990. Let's see what that gives us. Full number on my calculator, 0.75757. It looks like it's recurring, but there's no recurring symbol on my calculator. Makes sense to give an answer to 3 significant figures. So I'll give Spearman's rank as 0.758, and that's to 3 significant figures. Part B, test the editor's belief, use a 5% significance level and state your hypothesis clearly. So let's go back and look at what the editor's belief was. They believed that Shorter articles were more likely to be read than longer articles. So we're expecting shorter articles to have a lower read rank. So a lower number of words, lower read rank, a higher number of words, a higher read rank. So that is an example of a positive correlation. Now, because we know it's a positive correlation, we can now write H0 and H1. So H0, so remember this is always a test for zero correlation. So H0 is rho is equal to 0, and H1, because it's a positive correlation, rho is going to be greater than 0. We now need to find our critical value, and we can use the formula book. Now for our critical value, n is going to be 10 because that is the number of rankings that we have, and the significance level is 5%. So if we look at that in the formula book, we get 0.5636. So what I'm going to do is to draw a number line so I can physically see where the critical regions are. So I've got 0 at this end, and then 1 to -1. I've got my critical values. Let's just put them on here. So I don't need the negative one really, but I'll just put it on anyway. So we got 0.5636. Actually, let's take it off because Spearman's rank gives us whether it's positive or negative, so I don't need to do negative. And I'll shade here. So this is my critical region. This is where I'm going to reject H0. The value of my correlation coefficient was 0.758, which is in the critical region. It's going to be somewhere over here. So 0.758. So I can now get onto my conclusion. So I can say that since 0.758 is greater than 0.5636, we're going to reject H0, so reject H0. Now, do we need to write a big long sentence? No, we've just tested the editor's belief. The belief was H1, so we're rejecting H0, or which means that we're going to be accepting H1. So reject H0, therefore there is evidence to support the editor's belief. There is evidence to support the editor's belief. Question number 2. New recruits to Sonorep are given a 2-part test covering spatial and numerical skills. The scores on each part of the test are normally distributed. The recruitment manager believes that the mean score for spatial skills is more than the mean score for numerical skills and wishes to find a 95% confidence interval for the mean difference. She took a random sample of 8 recruits and recorded their scores on each part of the test. The results are given in the table, this table here. Part A, calculate a 95% confidence interval for the difference in mean scores between the 2 parts of the test. So for this part of the question, we're going to need the following formula. We need to be able to find the mean of the differences, the standard deviation of the differences, and then we're going to use this to find a confidence interval for the mean of the differences, where D is going to be the difference between the scores, N the sample size, alpha significance level, and T is the student's T distribution. So I'm going to start by saying let D be equal to the spatial skills test score minus the numerical skills test score. So numerical skills test score. The easiest way to do that with the table that I've got is just to add another row D and work out what those differences are. So it's basically going to be the top number, subtract the bottom number. So some of those differences are going to be negative. So 41 minus 35 is going to be 6. 38 minus 32 is also 6. 29 minus 31, negative 2. 45 minus 37, 8. 37 minus 38, negative 1. And then we're going to have 12, 0, and 10. Okay, so from this row I can work out the sum of the differences, which is actually 39, so I've worked that out already. So now I can work out the mean of the differences, which will be 39 over 8, n is 8, and that gives me a value of 4.875. Right, so let's highlight that because we don't want to lose the numbers that we need amongst all the other working. So now we're going to work out the standard deviation of the differences. So that will be the square root of, so we'll use this formula here, the sum of the differences squared. So let me just add another row, and let's do it here, of d squared. So I will have 36, 36, 4, 64, 1, 144, 0, and 100. Now the sum of those differences squared is 385, and I need to subtract from that n times by the mean squared. So the mean is this 4.875 squared. So n, actually I can replace n with 8. I know that's a number of observations, times by 4.875 squared, and that's all over n minus 1, so it's going to be all over 7. So work that on our calculator and see what we get. Now I've already worked this out, and I get 5.276294 and so on. When I come to use this in the formula here for these confidence limits that I can use for the confidence interval, I'm going to use the answer button for this value here to get it as exact as possible. Okay, let's put what we've got into this formula then. So the mean, so this is now for my confidence interval, basically the limits of the confidence interval, 4.875. Okay, so that's this value here, plus or minus. Now we need to look up values from the student's t distribution here. So we need to look up t, and the number of degrees of freedom is going to be 8 minus 1, 7. And we need to take the significance level and divide that by 2. Now remember, that's going to be 100 minus 95, which is 5%. So 5% divided by 2. So really I should have said here that it's 100 minus alpha divided by 2. So that's going to be 2.5%. Right, so let's get our tables and we'll look that up. In my formula book, it's on page 39, 7 degrees of freedom, 2.5%, and I get a value of 2.365. So I've got my difference plus or minus, the mean of the difference is 2.365. That's this part, and now I times that by the standard deviation. So this is why I want to use the answer button. So 5.2762 and so on over the square root of n. So it's going to be root 8. And let's see what two values we get. One when we do the minus and one when we do the plus. Now for my lower limit, I'll give you lots of digits for this one. So I get 0.463206 and for my upper limit I get 9.286793. So I'm going to give these to three significance figures. So I will have 0.463 and 9.29 as my confidence interval, and that's given to three significant figures. So I can be 95% confident that the mean of the differences should be between these two values here. Part B. State, given a reason, whether or not the confidence interval supports the recruitment manager's belief. So if we look back at the question, the recruitment manager's belief is that the mean score for spatial skills is more than the mean score for numerical skills. Now there's actually a problem with trying to support her belief, and the problem is to do with our confidence interval here. So if I were to draw this out, if I was to draw a normal distribution here and show what a confidence interval should look like, so 0 here with upper and low limits here, so that I can decide whether I'm going to accept H0 here or reject H0 in the tails here. Now can you see that this confidence interval here does not span or go across 0? What we've actually got, so if I draw out what this actually looks like, again with a normal distribution like this, and I'll have 0 in the middle like this. My two values, this 0.463 and a 9.29, okay, can you see that does not span across 0? That's what it should do. So putting this into a sentence, what we've got is, since the confidence interval does not include 0, it means that the mean of the scores of the two tests are likely to be different, so it does not support the recruitment manager's belief. Another way of stating that is that we're not going to be able to state a H0 because there isn't going to be that acceptance region that we talked about, because to have an acceptance region, what we need is for our confidence interval to sort of span 0, as we said, with these rejection regions either side. This confidence interval does not do that. The deputy manager treated these data as two independent samples and obtained a 95% confidence interval for the difference in mean scores of negative 0.67 to 10.42. Part C. Explain why this treatment of the data is not correct. So at first glance it seems like we've solved the problem of the confidence interval spanning 0. This does. But he said he's treated them, assuming this manager is a he, could be a she, as two independent samples. Now, are these samples independent? Each letter stands for a different recruit, and what we've got is one recruit doing both tests. Is that likely to be independent? One person sitting two tests? I don't think so. So let's put that in a sentence. So what we've got here is that since the same person sits both tests, the scores are not, or very, very unlikely to be independent. So that's why the treatment of this data as two independent samples would not be correct in this case. Question 3. George took a random sample of 8 apples from the tree in his garden. The weight, X grams, of each apple was recorded. The results are summarized by sum of X is 752, sum of X squared is 73,094. Part A, calculate a 90% confidence interval for the standard deviation, sigma, of the weights of apples from the tree in George's garden. Okay, so for this part of the question, we're going to need these two formulas here. So 1 gives us the confidence interval for the variance. Now we want a confidence interval for the standard deviation. So we will square root these values once we've worked them out. And also, because the question is asking for a confidence interval for the standard deviation, and we've got sigma here. So sigma represents the standard deviation of the population. So standard deviation of population. And whenever we're using a sample to find a confidence interval for a population parameter, then we need to use an unbiased estimator for the variance, which is what we've got here. So let's write down what we have. N is 8, alpha is going to be 10% because the significance level is 10, because the confidence interval is 90%, and we have the summary statistics. So the sum of x is 752 and the sum of x squared is 73,094. So let's start by working out the variance using our unbiased estimator. So s squared is equal to 1 over n minus 1, so that's going to be 1 over 7, times by the sum of x squared, which we have 73,094, minus n times by the mean squared. So n, which is 8, times by the mean squared, which is the sum of x, 752, over 8. So there's the mean, and we square it. So let's see what we get. I do get an exact value for this. So that's 2,406 over 7. I want to keep that exact value because I will need to use that in my formula here. Yep, so we don't want to round to the end. Next we have some chi-squared values to look up. Okay, so let's start with the first one. So we have chi-squared. The number of degrees of freedom is going to be n minus 1, which is 7. And the first one we're going to look up is going to be alpha over 2. So 10 over 2, so that's 5%. Let's see what we get for that. And that's 14.067. And then we want to look up the other chi-squared value. So that's going to be at 95%, 1 minus alpha over 2, 0.95. So 95%. And we'll look this up. In my formula book, it's on page 36. So we're looking at number of degrees of freedom, 7, 95%. And I see 2.167. So 2.167. All right, so let's highlight these because these are going to be the values that we put into our formula. So we're going to be using this up here. So let's just put big brackets and we'll do the whole calculation in here. So n minus 1 times by the variance, so that's going to be 7 times by 2406 over 7, and that's going to be over the chi-squared value that I had, which was the 5%, so that's going to be the 14.067. Now I can immediately see that these 7's going to cancel out, so that's going to make my work a little bit easier. And then for this end here, it's also going to be 7 times by 2406 over 7, but this time we're going to be dividing by the 95% chi-squared value, so that's 2.167. Again, the 7's cancel out, and what we need to remember is that we need to square root these because we want confidence intervals for the standard deviation. Right, let's work these out. So that becomes the square root of these two numbers here, 171.03 and so on, and then 1110.29 and so on. So let's do that. So that's going to give us these numbers here, 13.07 0.81, so on, and 33.3210, and so on. And then the final answers are going to be 13.1 and 33.3. That's because I've rounded them to 3 significant figures. So that represents my confidence interval for the population standard deviation sigma. Part B, state an assumption about the weights of apples from the tree that is needed to carry out the calculation in part A. Well, we have assumed that the weights of the apples are normally distributed. That's the key thing here, that they are normally distributed. Part C, state, giving a reason, whether or not the confidence interval in part A supports the assertion that the population standard deviation sigma is equal to 26 grams. Well, basically, since the 26 grams is in the 90% confidence interval, so it's greater than 13.1, it's less than 33.3, it supports the assertion that the population standard deviation is 26 grams. Question number 4. As part of a winter sports day, both boys and girls complete a cross-country course. The times taken in minutes by a random sample of 9 girls are given below. And we've got 35.6, 28.7, 23.4, 42.1, 38.9, 31.6, 34.7, 26.3 and 37.2. Part A, find unbiased estimates of the mean and variance of the times taken by the girls to complete the course. Now, because we have not been given any summary statistics, so in other words the sum of x or the sum of x squared, and this is only 2 marks, we would be expected to work this out on our calculator. So using the statistics menu on your calculator, type in the values, and what we're looking for, an unbiased estimate for the mean is x bar, and on my calculator I get x bar as 33.1666 and so on, like that. It looks like 6 recurring. And for unbiased estimate for the variance, I'm looking for s squared x. Now on my calculator that comes up as 37.77. Right, so I probably want to give my answers to maybe 3 significant figures. So I'll get 33.2 for my mean, and I will get for my variance 37.8. So perfectly acceptable on this type of question to use your calculator to calculate these values. The times, x minutes, taken by a random sample of 6 boys to complete the course are summarised by the following statistics. The mean, x bar, 27.45, and the variance, s squared x, 15.77. Part B, test at the 10% level of significance whether or not there is a difference in the variances of the times taken by the girls and the times taken by the boys to complete the course. State your hypothesis clearly. Now, to test if there is a difference in the variances, we need to use the F test. So the first thing I'm going to do is use this notation here. So the variance of the boys is going to be represented by sigma squared sub b, and the variance of the girls sigma squared sub g. Now H0 is going to be, and it always is, that there's no difference between the variances. So I'll just put the variance of the boys is equal to the variance of the girls. And because I'm looking to see if there's a difference, not whether one is greater or less than the other, H1 is going to be that the variance of the boys and girls is not equal to each other. Now we need to calculate our test statistic. So this is the F test. Now there are 2 degrees of freedom here, 2 numbers, and they represent the sample size -1 for each of the distributions. Now the number that goes first is going to be the distribution that has the larger variance. So if I compare the variances of the boys and the girls, The girls has the larger variance. So I look at the sample size, which is 9 minus 1, 8. So that's the first degree of freedom. And the second degree of freedom is the sample with the smaller variance, which is the boys. And that is a sample size of 6. So 6 minus 1, 5. So to calculate this test statistic, it's going to be the variance of the girls divided by the variance of the boys. So the first number relates to that first variance, the second number is the one that you're dividing by. So the girls, that was exactly 37.77 from the calculator. And for the boys, we were given that was 15.77. And that gives 2.395, and then there's a 0 after that. Now I'm going to look up the critical value, and this is going to be the F distribution table, and I look for the 8 and 5 degrees of freedom. Now, since this is a not equal to null hypothesis, this is a two-tailed test, so 10% we split in half, so I'm looking for the 5% value, and that gives me 4.82. Now this critical value here represents the maximum value that we would get from our test statistics before we reject 0. But our test statistics, 2.395, is less than that, less than this value. So we accept H0, and then we write our final conclusion. And that final conclusion would be that there is insufficient evidence of a difference in the variances of the boys and the girls. A sports teacher at the school believes that the mean time taken by the girls to complete the course is more than 2 minutes longer than the mean time taken by the boys. Part C, stating your hypothesis clearly, test the teacher's belief at the 5% level of significance. Now we need to know what type of test we need to do. In part B, we showed that there was no significant difference between the variance of the boys and the variance of the girls. Now, if we say that the variance of the boys and the girls is equal, and also that the population variance is unknown, this is the formula we're going to be using to calculate our test statistic. This is going to be the t distribution, and down here we've got SP, and SP squared is a pooled estimate for the population variance. So it's going to be a full hypothesis test, so we start with H0 and H1. Now I'll be using mu sub B to stand for the mean of the boys, and mu sub G for the mean of the girls. So H0. So the important bit is that they think that the girls are going to take 2 minutes longer. Their mean time is going to be 2 minutes longer than the boys. So H0 is going to be that the mean of the girls, because that's the higher value, minus the mean of the boys, or they think is the high value, is going to be equal to 2. Whereas H1 is going to be that the mean of the girls minus the mean of the boys, and what the teacher thinks is that it's more than 2. So let's start by calculating the pooled variance. Now I'll just go through the formula for that. So that will be the nx minus 1 times by the standard deviation, or sorry, the variance of x, and then plus the number in my second sample minus 1 times by the variance of that sample, and that's going to be divided by nx, so the sum of the numbers in the samples minus 2. So let's just substitute those values in. So for the girls, n is 9, so 9 minus 1 will be 8, times by the variance we got for the girls, which was 37.77 plus number of boys minus 1, so that would be 5, times by the variance of the boys, which was 15.77, and then we're going to divide that by the number of girls 9 plus the number of boys 6 minus 2, and that gives us 29.30846. So now we'll calculate our test statistic. So we're going to start with the mean of the girls, which was that 33.16 recurring number, and then subtract the mean of the boys, which is 27.45, and then we're going to subtract from that the difference between the means, the population means, which is 2. So mean of the girls minus mean of the boy equal to 2, so minus 2. Now we get to the bottom. So here we've got our pooled standard deviation, which is going to be the square root of this. So I need to do the square root of this 29.30846 number. And then that's going to be times by the square root of 1 over the number of girls, which is going to be 9 plus 1 over the number of boys, which is 6. And that gives us a value of 1.302591, so on. Now I'm going to look up my critical value. So as I said, it's the t distribution. Now I need to work out the number of degrees of freedom. So that is the sum of the number of each of the samples minus 2. So it's going to be 9 plus 6, which is 15, minus 2, which is 13. So 13 degrees of freedom. This is a one-tailed test, an upper tail test, 5% level of significance. So we go to our formula book, or your calculator if your calculator can work it out, and we get a critical value of 1.771. Now, since our test statistic, this value here, is less than a critical value and we're doing an upper tail test, we'll accept 0. Our value is not significant, so the teacher's belief is not supported. Part D, state an assumption about the distribution of the times taken to complete the course for the tests in Part B and C to be valid. Well, basically, the times to complete the course must be normally distributed. Course must be normally distributed for the test that we did in Part B and C to be valid. Okay, Part E. Explain the relevance of the test in Part B to the test in Part C. Now, I did go through this as we were deciding what test to use in Part C, and that was to do with the variances. We did a test in Part B that showed that there was no significant difference between the variance of the boys and the girls, and for the test in Part C to be valid, that must be true. So we'll just write that down. So the test in Part C requires that the girls' variance is equal to the boys' variance. So the test we did in Part B suggests that this is true. Remember, in Part B we showed that there was no significant difference between them. So the test in Part C is valid because of this. Question 5. Usanian Engineering manufactures bolts in large batches. The lengths of the bolts in millimeters follow a normal distribution with a mean 38 millimeters and a standard deviation of 0.3 millimeters. A random sample of 3 bolts is taken and the lengths measured. Find the probability that the difference between the mean length of the first 2 bolts and the mean length of all 3 bolts is greater than 0.2 millimeters. Okay, so let's highlight the important information. We've got normal distribution, mean of 38, standard deviation 0.3. We're taking a sample of 3 bolts and we want to find the probability that the difference between the mean length of the first 2 bolts and the mean length of all 3 bolts is greater than 0.2. So first thing I'm going to do is set up my random variables, and I'm going to say let B1, B2 and B3 represent the lengths of the 3 bolts. Let me now write down what the mean of the first 2 bolts would be. So that'd be B1 plus B2 divided by 2. And then the mean length of all 3 bolts, B1 plus B2 plus B3 divided by 3. And what I want to find is the probability that the difference between these mean lengths is greater than 1.2. So I could write down the mean length of the first 2 minus the mean length of all 3 is greater than 0.2. However, I could have written these probabilities the other way around. So I could have had the mean length of all 3 minus the mean length of the first 2 bolts. So because it could be this probability or it could be the other way around, I need to multiply this by 2, because basically I'll be doing 2 lots of the same type of calculation but with these 2 flipped around. So I'll put the 2 in front to show that. Now what I'm going to do is I'm going to put all of this bit together by putting all of those B1, B2, B3 over the same denominator. So if I take the first fraction and I multiply the numerators by 3, I'll get 3B1 plus 3B2. Then for the second fraction, I'm going to multiply these numerators by 2. So I'll get 2B1 plus 2B2 plus 2B3. And then all of this is going to be over a denominator of 6. And that needs to be greater than 0.2. Now the next thing I'm going to do is to combine all of these numerators and then times both sides of this inequality by 6 to get rid of that. So then I'll have 2 lots of the following probability. So let's combine these. So I'll have 3B1 minus 2B1, which is just B1. 3B3 minus 3B2 minus 2B2 leaves me with just B2, and then minus 2B3. So minus 2B3 times in both sides by 6 means that the inequality now becomes greater than 1.2. Now I'm going to let x equal this combination of this random variable, of these random variables, and I'm going to use the rules for the combinations of random variables to work out the mean of x and the variance of x. So let's start with the mean of x, e of x. So e of x is going to be equal the mean of b1 plus the mean of b2 minus 2 lots of the mean of b3. They're just the standard rules for combinations of random variables. So the mean of these will be the mean of the population. So it's going to be 38 plus 38 minus 2 times 38 leaves 0. So that means that I have a value of e of x equal to 0. Now let's work out the variance of x, and that will be the variance of b1 plus the variance of b2 plus, even though it's a minus, remember the rules for variances, plus, and this is like my a, so a squared, which is 4, so 2 squared times the variance of B3. Now up here we have the standard deviation, which is 0.3. So the variance is going to be 0.3 squared. So if we put 0.3 squared in here, so the variance of x is going to be 0.3 squared plus 0.3 squared, because the variance of B2, plus 2 squared times the variance of B3, which is also 0.3 squared. And that gives 0.54. Not 0.5 to the power 4, 0.54. Okay, now I know that x is normally distributed because we're talking about the population now. And it has a mean of 0. I guess I should have highlighted here that the variance of x is equal to 0.54. So mean of x is 0. Variance of x is 0.54. You could write that as the square root of 0.54 squared. And what we want to do from this, we want to find the probability that x is, we go back to here, greater than 1.2, because x represents b1 plus b2 minus 2b3. We're going to work this probability out, and then once we've done that, we need to multiply it by 2 to get our final answer. Right, so using normal CD, we get 0.05123552. We want to times that by 2, remember, because we already decided that there are 2 ways in which we can have these differences between these mean lengths. So let's go to menu and just take our answer and times it by 2. The full number that I get is 0.10247704 and so on. We want to give an answer to 3 significant figures as usual, so 0.102. So that would be our final answer for this question. Question number 6. The continuous random variable x has probability density function f of x equal to 1 over 2 pi times by 1 minus cos x when x is greater than or equal to 0 and less than or equal to 2 pi, or 0 for any other value of x. Is what we call a piecewise function. Part A, sketch f of x. Okay, so what we're going to do is we'll try and do this bit by bit. If you've got a graphic calculator, I guess you can sketch it. But let's start with the cos x first of all, and then we'll apply different transformations to that. So we'll start with cos x between 0 and 2 pi, which is going to look like this. Then we'll do with the minus in front of the cos. Okay, so that will basically flip the graph in the x-axis. So it's now going to look like this. So I'll get rid of the first one. So this is now the graph of negative cos x. Now we've got basically plus 1 minus cos x, so the whole graph is now going to move up by 1. Now this is at negative 1, it was at 1 before, so we'll just shift the whole graph up. So it's now in this position, like this. And I'll get rid of this one. So now we've done the 1 minus cos x, so that's what this graph looks like. So we've got 2 pi here and 0 here. And this last bit, the 1 over 2 pi, that's basically going to be a stretch of 1 over 2 pi in the y direction. Now if I have a look at what the y direction value is, so at the top here, this is now 2 because it would have been originally at 1 when the graph got flipped over, so it's minus 1, then it became 1 and then moved up to 2. And what we're doing here, we're dividing that by 1 over 2 pi. So basically we've got 2 over 2 pi which is the same as 1 over pi. So let me now draw a nice clear sketch of that now that I know what it looks like. So I'll have my x-axis down here, I'll have my y-axis or f of x axis here, and let's sketch my graph. Looks a little bit like a normal distribution, I guess. So it's going to be this type of shape. We'll have 2 pi here, 0 here, and the top of this will be 1 over pi, because we said it was 2 over 2 pi, so 1 over pi will be the maximum value. Now, since this is 0 otherwise, there is no other part to this graph. Okay, part B. Use algebraic integration to show that e of x squared is equal to 4 pi squared over 3 minus 2. Okay, so to do this part of the question, we need to use this formula here to find e of x squared. So e of x squared will be equal to, now our limits are going to be 0 and 2 pi, of x squared times by f of x, which is 1 over 2 pi 1 minus cos x dx. Right, so first thing I'm going to do is I'm going to bring the constant over. So I'll have 1 over 2 pi in front of the integration sign, and then 0 2 pi. And if I then expand the brackets of what I've got left, that'll be x squared minus x squared cos x dx. Now, to do this part here, I need to do integration by parts twice. So let's do that down here, and then once I've got the answer, I'll then sort of clear the working out. So I know that I'm going to have 1 over 2 pi, and then it's going to be this integrated, which will be 1/3 x cubed, and then it will be minus the result of this integration by parts twice. Right, so let's start with u equals to x squared, dv dx equal to cos x, so du dx is going to be 2x, and v is going to be sine x. So integration by parts once will give me uv, so x squared sine x, minus the integral of v du dx, so that's these two times put together, so 2x sine x. Okay, so I need to do integration by parts to work out what this part of my answer is. So we'll do that here. So u this time is going to be x, dv dx is going to be sine x, du dx is 1, and v is going to be minus cos x. So let me write down the full answer. So I've already got this x squared sine x from before, minus 2 lots of doing integration by parts on this part here. So that would be uv, so that would be minus x cos x, minus x cos x, then minus the integral of v du dx, which is 1 times by negative cos x. So if I put the plus there, I can write this as cos x dx here. Right, so this gives me a nice straightforward integration here. So this was going to become sine x. So let me write down the full result of doing integration by parts twice on this, and I get, let's work it out and then simplify it as we can. So x squared sine x. Okay, so that's this bit, and then I'll expand and simplify as I go. And then negative 2 times by this, so this will give me plus 2x cos x, so plus 2x cos x, try and write that neatly, 2x cos x, and then we know that this bit integrated is going to give me sine x. So then if I finish the rest of the expanding, I'll be -2 times by sine x, so -2 sine x, so -2 sine x. Okay, so that's the result of this integration. Okay, so now let's substitute this into here. Now I need to subtract all of this, so it's going to be minus x squared sine x, and then minus 2x cos x. Always miss the c out when I do that, x like that, so minus 2x cos x, and then plus 2 sine x. So I'll have to do it down here, so plus 2 sine x, and my limits will be 0 and 2 pi. Okay, we'll start by putting the limits of 2 pi into this. So you've got 1 over 2 pi times by, now this will be 1/3 times by 2 pi cubed minus, now if anything becomes 0 I'll probably leave it out. So here I'll be subtracting, well, we got sine of 2 pi, which is 0. Let's just put -0. And then we'll have minus 2 pi times by cos 2 pi. Now cos 2 pi is 1, so you'll end up with minus 2 times by 2 pi, so minus 4 pi. And then here again, sine of 2 pi is going to be 0, so I won't bother with that. So okay, we've got our first bit done. Now we'll substitute in the 0. So when we substitute in 0, there's nothing here, so just put 0. Now sine of 0 is 0, so there's going to be nothing here. Cos of 0 is 1, so we'll basically have minus 2 times by 0, oh well, that's gone, and times by 1, so that's gone, and then 2 times by sine 0, well, there's nothing there to write either, so basically just all zeros. Right, let's simplify this and see what we get. So you've got 1 over 2 pi, and then in the brackets, this bit here will become 8 pi cubed over 3. So 8 pi cubed over 3, and we're subtracting 4 pi. So what we're going to do now is divide everything in the brackets by 2 pi. So if we do divide this by 2 pi, we'll get 4 pi squared over 3. And if we divide this by 2 pi, 4 pi divided by 2 pi is just 2, so minus 2. So we get the result as required. Part C, hence find the standard deviation of x. So the standard deviation of x is going to be the square root of the variance of x. Now the variance of x, that's going to be e of x squared. Now we worked out e of x squared in part B minus the mean squared. Now because we've got a sketch of the graph, if the graph is symmetrical, we can find the mean by symmetry, and this is symmetrical because it came from the graph of cos, and because we've got 0 and 2 pi here, by symmetry we can say that e of x is pi. Right, so e of x squared is equal to 4 pi squared over 3 minus 2. Okay, so that was from part B. And then we've got e of x is equal to pi, and we get that by symmetry. Okay, so we can go on to say that var x is equal to 4 pi squared over 3 minus 2, and and we want to subtract pi squared because that's the mean squared, so minus pi squared, and then we're going to square root that to get the answer, to get the standard deviation. So I'll do that on my calculator and just work that out and then square root it and see what I get. So standard deviation is coming out as 1.28986. Let's square root that and see what we get. So that's coming out as 1.135723. We want to give that to 3 significant figures, so we'll go for 1.14 to 3 significant figures. We could give a more accurate answer, but that's the sort of standard amount of accuracy we want to go for, 3 significant figures. The lower quartile of x is 2.31, correct to 3 significant figures. Jeff suggests using a normal distribution with the same mean and standard deviation as x to estimate the interquartile range of x. Part D, find the percentage error of this estimate. Right, so the first thing we're going to do is to work out what the actual interquartile range is using the information that's been given. So we've been given a lower quartile as 2.31, so after I mark that on my sketch, that's here 2.31. So I know the space between the mean and the median actually is this size. So the upper quartile is going to be equally spaced on the other side because it's a symmetrical distribution. So the interquartile range is basically going to be this much. So I could say it's the difference between pi and 2.31 doubled. So the actual interquartile range is going to be 2 lots of pi minus 2.31. And that comes out as 1.66318 and so on. Now I don't want to round this. I'm going to use this because I want to find the percentage error as closely as possible. Now the second bit I'm going to do is to find this estimated interquartile range using the normal distribution. So we're going to use inverse normal on our calculator. So first of all, I'll put in an area of 25%. So this is to find the lower quartile. And we're using mean of pi, and we're using the standard deviation that we worked out before, 1.135723. And that gives me a value of 2.3755559 and some more digits. And I'm just going to go back and change the area now to 75% to get the upper quartile. Same mean and standard deviation, and I get an upper quartile which is equal to 3.907625 and so on. So let's find the difference between these two to find the interquartile range, and what I get is a value of 1.5320 and then 6. Now I can work out the percentage error. So that's going to be the difference between my two amounts. So that's going to be 1.66318 minus 1.53206 divided by the actual interquartile range, and that's the 1.66318 number. And then all of this I need to times by 100 to change it to a percentage. And that gives me 7.8836%. So we'll go for 3 significant figures and we'll go for 7.88%. as this error between the actual value and this estimated value using the normal distribution. And I guess the reason why it's done that is because I think at the start I say it looks a little bit like a normal distribution that we have here. Question 7. A local Chamber of Commerce researcher collected information from a random sample of 8 new retail companies. The number of employees, M, and the company turnover in 10,000s of pounds, T, was recorded for each company. The results are summarized below. So the mean of M is 8, the mean of T is 62. We've got the summary statistics SMM 246, STT 20,416.16 and SMT 2076.8. Part A, calculate the product moment correlation coefficient for these data. So this is the formula here that we would use to find the PMCCR. The formula has X and Y, we've got M and T, so what we're going to do is to take the X's in the formula, replace them with M, and the Y's in the formula, replace those with T. So that means that the value of R is going to be equal to SXY, which is SMT in our case, 2076.8 divided by the square root of SXX, which is SMM, 246, times by SYY, which is RSTT, and that's 20,461.16. And from my calculator I get 0.925682 and so on. We'll give that to 3 significant figures, so 0.926, 3 significant figures there for the value of the PMCC. Part B, stating your hypothesis clearly, state at the 5% level of significance whether or not there is a positive correlation between the number of employees and the company turnover. Okay, so we'll start with H0 and H1. So H0 is going to be that rho is equal to 0, and H1 is going to be that rho is going to be, since we're looking for a positive correlation, that rho is going to be greater than 0. So since n is 8, the significance level is 5% and it's one tail test, we can use this to cut the critical value. In my formula book it's on page 37, so I go to n is 8 and 5% significance level, and I get a critical value of 0.6215. I like to do this by drawing a number line just to make sure I don't make any mistakes. So we'll have 0 here, 1, minus 1. We've got a critical value of this 0.6215. So here's my critical region. This is where I'm going to reject H0. And I've actually got a value of R which is well into this critical region here. So my conclusion is that I'm going to reject H0. Well, that's not a conclusion, but I'll say what I'm going to do first. And the reason I'm rejecting H0 is because 0.9256 is greater than my critical value, 0.6215. And now we write our conclusion. Therefore, there is sufficient evidence of a positive correlation. You can sort of tell that actually from the value of R we get. Positive correlation. It needs to be in context. So what's this between these values of M and T, which is the number of employees and the turnover? So sufficient evidence of a positive correlation between the number of employees and the turnover. Number of employees and the turnover. Steve owns a small retail company and is thinking of increasing the number of people he employs. He believes that there may be a relationship between the number of employees and the company turnover, and he wants to use this to estimate the change in turnover. Part C, Part I, Part 1, state, given a reason, the form of a suitable relationship Steve can use that is consistent with your answer in Part B. Now I would say that since we've got evidence of a positive correlation, in fact looks like a strong positive correlation, a suitable relationship would be a linear one. So since we have evidence, because we did that hypothesis test, we got some evidence of a positive correlation. Even if it's a negative correlation, it'd be a linear relationship of a positive correlation. A linear relationship would be suitable. Part 2 or Part I of Part C, find the equation of this model. Now I've added the summary statistics that we were given at the beginning of the question, and we can use these to find the equation of the model. Now from the formula book it tells us that B is equal to SXY over SXX. And remember I said that we were replacing X with M and Y with T. Now if you're not sure which one to replace with which, X is always going to be the independent variable or the explanatory variable. So this is the one that causes Y to change. So let's think about it. Is it the number of employees that changes the turnover, or is it the turnover that changes the number of employees? Well, it's the number of employees which causes the turnover to change. So X has to be the number of employees. So just think about which one is the explanatory or the response variable, and which one is the independent variable or response variable. So Y has to be the turnover. So if you're not sure which one should go with which. So yeah, in our question, SXY will be SMT and SXX will be SMM. So the summary statistics that we got at the very beginning of the question, so SMT 246, SMT is the 2076.8, SMM 246, and I think we'll leave it like that for now. We'll work out in a moment because we now need to work out A, and A is equal to the mean of Y, again this is from the formula book, minus B times the mean of X. So A will equal the mean of, in our case, T, minus B, so that's what we've just got here, times by the mean of M. So we'll put those values in and see what we get for A. So mean of T, 62, minus B, so that's the 2076.8 over 246, times by the mean of M, which is 8. Right, so let's see what we get for A. Okay, so this gives us negative 5.5382, and I guess I probably want this value here given in decimal places, because when I give the equation, I want to give those values in the equation to 3 significant figures. So it looks like my value of B is 8.4422. So I can now write the model. So it's going to be T, which is the turnover, is equal to A, and I'm going to give these the 3 significant figures. So negative 5.54 plus b times m, so plus 8.44 m. So there's my answer for this bit, and I'll just put a note here that A and B given to three significant figures. And part D of this question asks us to use this model to estimate the change in turnover in pounds if Steve increases the number of employees from 13 to 16. Now we don't need to put 13 and 16 into the whole equation. The only bit that's going to change is this part here, and m increases by 3, so we'll just increase m by 3, and actually all we need to do is put 3 for m because it's linear. It doesn't matter which two values I put in, the increase is going to be the same. So substituting m equal to 3 just into the 8.44 m part, because that's the part that's changing. So 8.44 times 3, 25.32. Now remember, t is in, I think, tens of thousands of pounds. So I want to get the turnover in pounds. So that's the value of t. So if I times that by 10,000, what I get is 253,200 pounds for that increase in turnover. According to this model, if he gets, or if Steve gets 3 more employees from 13 to 16, or in fact any increase of 3 employees, if it was 100 to 103, the increase in turnover is still going to be the same amount. So continuation of question 7. The residuals for the model Steve used are given in the table below. So we've got the number of employees and the residual figures given here in the second row of the table. Figure 1 shows a sketch of Steve's model here. Part E, on figure 1, sketched a scatter diagram for Steve's data. Now the residuals are going to be the differences between this regression line and the actual observed values. So those which have a positive residual is going to be this amount of space above the residual line, and any that are negative are going to be below the line. So I guess the first thing we need to do is to work out how much each square is worth here on this scale. So we've got 5 squares for 20, so each square is going to be worth 4. So we're going to start off with 1 employee. So 1 employee, I think it's going to be 2.5 squares across. Let's have a look. So how many squares we've got for 2? 1, 2, 3, 4, 5 squares going across. Yep, so 2.5 squares across for 1 employee. 1, 2.5. Then we've got 2 employees here, 3, 4, and so on up the scale, 5, 6, like that. Right, so starting with 1 employee, we've got a residual 26.6. So if each square is worth 4, we're looking at about 6 squares above this point here. So it's going to be a bit of eyeballing, really, can't get it exactly, particularly as this residual line doesn't go all the way to 1 employee. I guess I could extend it to help me do it like this. And is it going to go far enough at the other end? Yeah, that's fine. So yeah, 6 squares above this point. So it'll be roughly this type of position. And we've got another one, a residual of 13.5. Each square is worth 4. So we're talking about 3 and a bit squares above here. So roughly this position here. I'm going to complete the rest. When you do this type of question, there'll be some sort of overlay that they put on the top that will sort of give a sort of range of values for where you can plot your X's. So I'm just going to do the remaining ones, or maybe I'll do one more. So this one here, a negative residual, so above 4 employees, it's going to be about 2 and a bit squares below our regression line. Here we go, and I'll do the remaining ones. Okay, so this completes my sketch of the scatter diagram based on these residuals and the number of employees. Notice, as I said, those with a positive residual are above the line. Those with negative residuals are below the regression line. Part F. Use your scatter diagram, which is here, and the table of residuals, which is here, to refine the model and calculate a revised estimate for your answer to Part D, which is here. Explain clearly how you calculated your estimate. Now, from Part D, we calculated this increase in turnover based on the fact that Steve was going to increase his employees from 13 to 16. Now, if you have a look at our residual table, it looks like those companies that had between 13 and 16, so they're going to be in this part of the table. The regression line underestimated the turnover, and the actual turnover was above that. So we want to use these residuals here to come up with a revised turnover figure, which I suspect is going to be higher than the value that we got here. So we're going to find the average residual for the 14 employees and 18 employees, because that's where the 13 and 16 is roughly. So average residual for 16, it's actually 14 to 18 employees. Well, that's going to be 9.8 and then plus 21.9 divided by 2, and that gives us 15.85. So this is telling us that we want to increase T by 15.85, which means increasing the turnover by that number times by 10,000. So we want to increase the turnover by 158,500. So if we now add that to the 253,200 figure, that gives us, and this is only an estimate, so I've got 411,700, so we might want to call it, I don't know, if we go for 3 significant figures, 412,000, something like that, as this revised figure for the turnover. And I just realised I need another 0, 412,000, not 41,200. So that will be my revised figure based on the residuals, that around that number of employees, our regression line is underestimating the actual turnover, whereas for some of these figures in here is overestimating the actual turnover. Okay, given that there are 4 positive and 4 negative residuals, part G, find the probability that a random pattern of residuals is plus plus, minus 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 minus, plus plus. Now what I'm going to do is I'm going to use P to stand for a positive residual, and rather than use N for negative, because that can be used for other things, when we're dealing with probabilities like this, we tend to use P and Q. So Q is going to stand for a negative residual, and this is like a little bit like a binomial. So what am I looking for? Well, I want this one option of where I have 4 positives and 4 negatives. So if I write that as a probability, that's going to be P to the power 4, positive, 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 and 4 negatives, so Q to the power 4. But there are lots of different ways of getting 4 positive and 4 negative residuals, and to calculate that I need to use 8C4. So I've got 8 residuals and I want to choose 4 of them and I want those 4 to be 4 positive and 4 negative. Now you can see straight away what happens is that all of this P stuff cancels out, so we actually end up with just 1 over 8C4. So I'll calculate, and that's 1 over 70. So we actually didn't need the probabilities of P and Q because they cancel out. So part G, what we have is 1 over 70. And the last part here, with reference to your answers to part A and G, suggest what Steve could do to investigate further. So it looks like this here was G. Have I labelled up my answers wrong? So G was 1 over 70. Now this was F, wasn't it? So what happened to my answer to part E? Oh, E was this, wasn't it? Drawing the residuals. So let's put that as E. Now the reason I've relabeled it because I want to look at my answers for part A and for part G. So what have I got from part A? I've got a value of R, PMCC of 0.926, which is suggesting a positive correlation. And then for part G, I've got the probability that I'm going to get this particular pattern of residuals, which is what I've got here, is only 1 over 70. So putting these 2 bits of information together, we've actually got quite a low chance. Now 1 over 70 is just over 1% chance of getting this pattern of residuals, which is quite low. So what can Steve do to investigate further? Well, I think the obvious thing is that he needs to collect more data. Yeah, he's only looked at I think it's 8 different companies he was looking at. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, quite a small sample size. So I would say that he should collect more data by looking at more was it companies or factories? I think it was companies, more companies, as he has only taken a sample of 8 companies. And that completes this further statistics 2 paper.